Conference at the University of Michigan, and he's working with Dr. Jiang to use deep learning to reconstruct brain MRI images. He's interested in reinforcement learning and neuroscience foundation of AI. We are very happy to have him here. He is going to talk about deep learning for brain MRI reconstruction, expanding the unit. Thank you again, and can I start?
Yeah, so my name is Makarand. Thanks for the introduction. Yeah, I'm a first-year master's student in computer science at Michigan. And so I'm talking about some work that we did with using deep learning on accelerating MRIs to essentially make MRI acquisition faster. Using magnetic resonance imaging on the brain, or MRIs, can help with investigating, as we've seen, the structure and function of the brain, and even for neurological diagnosis. But the output of the MRI isn't actually an image, but Fourier domain data, or what's called a K-space. And it can take a very long time to acquire these scans. Patients often have to sit for over 30 minutes, completely still, and motion can add artifacts. And so it's cost prohibitive and expensive in time. And often modern MRI machines have multiple coils that acquire many different K-spaces simultaneously. So how to reconstruct an image from the output of an MRI is we get these multiple K-spaces, so C for the number of coils, and then we can inverse Fourier transform them to get C images. And then we can use the root sum of squares, which is essentially like an average, to compute a single image. And that's what's used for the final output. But acquiring these K-spaces can take a long time. So what if we could undersample those K-spaces and not acquire as much data? Well, if we undersample the K-spaces, like as you can see on the left, there's a lot of holes where we're not acquiring data. If we try to inverse Fourier transform them to get images, we get these repeated artifacts and blurred noise, so that when we construct this final output image, it's not really appropriate for any sort of usage here because of all of this noise. So the upshot is that we can use methods that rely on prior knowledge about what the reconstruction is, what the image is going to be. Like, for example, if we know that it's going to be a brain, we have some prior knowledge about what the image is going to look like, to try to construct an acceptable image using statistical reasoning. So machine learning, specifically supervised machine learning, we can use to train a statistical model if we have labels or correct answers to our question. So what we can do is create a model that can take in K-spaces that are undersampled from all the different coils, output a single image, and then compare the reconstruction that that model does with the reconstruction that we would get if we use the fully sampled K-space. So we train these models on the FAST MRI dataset, which is an open dataset used for brain MRI images. And we can evaluate the quality of the images using the structural similarity index measure, which we can use to compare how similar two images are. Now, this isn't a perfect metric, but it does seem to correlate with what neuroscientists and radiologists seem to look for in terms of the quality of reconstructions. So a very common and popular model is the UNet, which is an image-to-image convolutional neural network, which is kind of put in at the end of this reconstruction pipeline. So the CK spaces turn into C images, which is then compressed into one image, and then is given to the model, and then which removes the noise that we can use for, and then output something appropriate. However, this doesn't really, this may be losing information from the multi-coil nature of the data, because the UNet only gets the input by the time it's already collapsed into a single image. So regardless, it still produces some quality reconstruction. So with 7 million parameters in our model, we can create a 0.92 SSIM approximately reconstruction. So if you look at these images, you can see the structure of the brain is preserved, but some of the finer details are lost. Now, I'm not a radiologist or a neuroscientist, so I can't really comment on how precise these reconstructions are, but I can see that some noise is added in reconstructing these. So we experimented with applying the UNet at different parts of the model of the image reconstruction pipeline. So our K-UNet, or K-space UNet, operates directly on the K-space data. Now the UNet is intended originally for imaging data, so we wanted to see if it would work for the K-spaces, which is a very abstract domain. So the CK spaces come in, are fed to the model. We get CK spaces out, ideally with some with those gaps filled in, which are then turned into images and then final image. And we can see that the KUNet produces images that do have artifacts, but achieve an SSIM around 0.86. So you can see that the overall structure of the brain is preserved, but there are some blurring and noise. So this is kind of like a proof of concept for being able to operate directly on the Fourier domain data. Next, we tried the I-UNet, or the images UNet, which operates on the multiple images directly and outputs that many images. So this is intended to hopefully take into account the multi-coil nature of the data before it gets collapsed into a single image, so that it may take advantage of the varying sensitivities of the coil in capturing. So the performance of this was around 0.74 SSIM, but you can see that while the brightness kind of varies in the reconstructions, some of the finer details of the brain are preserved, more so than the K-space UNet did. So in combining some of these models, if we combine the K-UNet and I-UNet into a larger ensemble model, so where the CK spaces turns into, or goes into the K-UNet, and then is turned into images, which is then fed to the I-UNet, and then finally collapse into a single image, we're able to achieve images that have little noise, still don't have quite the precise detail as the targets, but are able to construct the images with the same structure of the brain. And this is around a 0.88 SSIM. Now, if we combine the I-UNet and the UNet, so keep in mind that the original UNet has 7 million parameters to it. If we combine the I-UNet and the UNet, then we're able to achieve a performance a little bit better than the 7 million parameter UNet with only 2 million parameters. So with 1 million to the I-UNet and then 1 million to the regular UNet, so with like a 2/7 parameter cut, we can achieve an SSIM that's slightly better. And you can see in the images, the detail is preserved more or less, and the structure of the brain, and there aren't really too many artifacts. So this is like a promising direction in reconstructing images. So the conclusion here is putting the model in different parts of the pipeline may allow the model to take advantage of information that could be lost in, say, collapsing multi-coil data or the transformations involved. So multiple models throughout this pipeline could also help stabilize the training and the image reconstruction quality. So further experiments in this vein may involve varying the combinations of models used in reconstructing and seeing how we can cut parameter sizes to create a model that is lightweight yet is able to reconstruct images of high quality. So thanks to Neuromatch for hosting this.
Thank you so much, Makarand. That was great talk. By the way, we are able to allow you to come for the attendees to come here and speak directly to Makarand. So if you want to do that, just ask us to give the permission. That was a great talk. Thank you so much. Do you know how, like you said about the UNet, KNet, and INet, do you know like how we can compare them if we have image, like which one we should choose? I'm pretty sure it's a little bit loose question. You don't know exactly, you need expert, but do you have any idea what's the best way to start?
Right, so what we used as a metric was the SSIM, which is, I think, originally intended for like regular images, not really medical images. So there isn't really a great metric for automatically evaluating reconstructed images, which is why certain, like a lot of these tasks will rely on actual radiologists going and looking at the reconstructed images and evaluating them for diagnostic quality. So there really isn't a great automated metric, but SSIM seems to be, I think, the most prominent right now.
I see. And do you use any trick or something for the implementation that you had for this work, like for this unit?
So this was implemented in Python with PyTorch, and we ran these on GPUs using our University of Michigan computing clusters.
It's not pre-trained, right?
They're not pre-trained. We had to train them. It would take around several hours to train the models, but once trained, it's using the models is very easy, especially with the lower parameter ones.
That's awesome. We have 4 minutes still. Feel free to ask a question. That's great. Do you have a GitHub or something to work on the images that you generated today?
Yes, I can link that in the chat.
That would be great. Yes.
I have a question as well, if you don't mind.
Sure.
Sure.
Well, first, I mean, I love the overall idea of using kind of anatomically informed priors to help your model. Since you're doing that, do you predict that the model would perform worse for kind of brains with lesions or tumors or something like that?
I think that's the real issue, is that because it's based on these priors, it might perform worse for I guess outliers, but it's hard to get, I guess, data for that. But I suppose that I guess the thing to investigate would be, are those lesions and anomalies would they even show up in the case space that's input at all? Because if it's not, then there's no hope for the model to be able to reconstruct that. So I think if there is a suspect for some sort of an anomaly, then you'd have to maybe sample a little bit more or be a little bit more thorough with that.
Thanks.
But these were from the healthy data set, right?
For which data set?
The images that you showed, these are from the healthy subjects.
Yes.
Okay, I just had a question on the data set. Are there, or do you know if there are data sets that are just more broad in the sense of having data from patients that have neurological disorders or maybe had lesions or things like that?
Yeah. So there really haven't been large-scale data sets for MRI reconstructions. Until very recently, the fast MRI data set is kind of, I think, the largest MRI, brain MRI data set that's available. But in terms of those specific things, I'm not sure of any large-scale data set that's able to do that. I think one of the drawbacks of machine learning is that it does rely on large amounts of data, which is maybe hard to acquire.
Gotcha. Thanks.
Was that the fast MRI, the data that you used
yes,
here, right?
Fast MRI, yeah.
And yeah, interesting. So it doesn't have the unhealthy data set. Thank you so much. With that, let's wrap up this talk. Thank you so much again for your great talk. And let's move on to the last speaker.